Welcome to Theory of Computation. This is lecture number 26. Well, what we are studying is complexity theory and the theory of NP completeness. And our goal is to finally prove the Cook-Levin theorem. We have discussed the Cook-Levin theorem and what it says. Cook-Levin theorem talks about an extremely important problem in theoretical computer science called satisfiability. And this theorem says that satisfiability is NP complete. What that means is that every problem which is in NP, every language which is in NP can be reduced in polynomial time to satisfiability. Thus, this is a problem that captures the whole complexity of the class NP. Let us also recall what NP is. Remember that NP is the non-deterministic analog of P. P is the set of all problems that we can solve in polynomial time, whereas NP is the set of all problems that can be solved by non-deterministic Turing machines in non-deterministic polynomial time. Let us once again emphasize that non-deterministic time does not correspond to any practical notion. It is simply a mathematical concept which captures a very interesting class of problems. What our goal is to prove that satisfiability is NP complete. This is the celebrated Cook-Levin theorem. This is a very important part of this course. Every complexity theory student, every graduate student should know this theorem, should be comfortable with the notion of NP and NP completeness, should be able to identify NP complete problems, and you should also be able to reduce problems and show that problems are NP complete. That not only has theoretical value, but it's also of extremely important practical value. NP complete problems arise a lot in computer science. If you're working on databases or operating systems or scheduling algorithms, you run across a lot of problems for which you try to find polynomial time algorithms. And some of those problems turn out to be NP complete. What that means is that these problems are so difficult that everything in the class NP reduces to these problems. Thus, if you prove that a problem is NP complete, you give a very strong evidence that a polynomial time algorithm may not be possible. At least you give a proof that if you were to find a polynomial time algorithm for that problem, then the class P will equal to NP, and thus working on that problem will require a lot of effort. And so you give very strong evidence that the problem is hard. Though no one has been able to prove that P is not equal to NP, however, proving that a problem is NP complete does constitute of very strong evidence that the problem may not have a polynomial time algorithm. Well, what we want to do is start by understanding the Cook-Levin theorem, which says that SAT is NP complete. This is a difficult theorem. This is a theorem that requires us to have a grip on several concepts at the same time. We need to understand the problem of satisfiability very clearly. We need to be very clear about the notion of reducibility, and we also need to be very clear about the notion of non-determinism. All these three ingredients are put together and some brilliant ideas to get this lovely theorem that we call the Cook-Levin theorem. In order to understand Cook-Levin theorem, what we will do is first prove that a problem that we call three-color can be reduced to satisfiability. So in some sense we will prove a little theorem today. That theorem will say that one particular problem in NP that we call three-color or threecolorability is reducible to satisfiability. The Cook-Levin theorem is a much more general and a much more stronger statement than that. the Cook-Levin theorem says no matter what problem that you take in NP can be reduced to satisfiability. Well, today's lecture, the goal is that you should become comfortable with the problem of satisfiability, and you should be able to translate at least little problems into the question of satisfiability, and today we will see an example of that. Then in the next lecture we will start proving the Cook-Levin theorem, and hopefully you will understand that because you will have a bigger grip on the question of satisfiability. So let us review a few of the notions that we need for this theory. It's good to go over them again so that we know concretely what we are trying to do. Recall that we were talking about NP completeness. You remember that the class NP is the set of all easily verifiable problems. All problems that have polynomial timed verification algorithms are problems in the class NP. In fact, NP is by definition the set of all easily verifiable problems. A problem is called NP hard if every problem in NP can be reduced to it. So for a problem to be NP hard, it must have the property that no matter what language you take in the class NP, you should be able to find a polynomial time reducibility to this problem. In that case, we say that the problem is NP hard. And you would notice the word hard here is actually trying to hint that the problem is difficult. Well, of course, the problem is difficult, because if you were to solve that problem in polynomial time, you would have solved every problem in NP in polynomial time. So in some sense, the whole hardness of the class NP is contained in that one problem that we call NP hard. Then we talked about NP completeness. A problem is called NP complete if it has two properties. One, it has to be NP hard, and the second thing it has to be is it should be itself a member of the class NP. That's a very stringent requirement. So the question whether there are NP complete problems is not a simple question. The existence of NP complete problems is not clear from the definition. We can define mathematical objects. However, sometimes our definitions can be so bizarre and they may demand so much out of problems or structures that we are defining that those things may cease to exist, or those things may not exist. In this case, we are saying that we will call a problem NP complete if it is NP hard and also a member of the class NP. It's not at all a priori clear that such problems should exist. And of course, such problems do exist. This definition is not just useful, but it's extremely useful in computer science. There are thousands of NP complete problems, but to prove that they exist, we will need the Cook-Levin theorem. So let us continue with our definitions. Recall that A is NP hard if for all B in NP, B is polynomial time reducible to A. Let us also recall that a language A is called NP complete if A is in the class NP and A is itself NP hard. So now what we want to do is we want to talk about NP completeness and satisfiability. It is not clear at all that there are NP complete languages. In fact, if they exist, that would be an extremely amazing fact. These languages have all the complexity of the class NP. They will be extremely important because of the following theorem. This theorem says that suppose if A is NP complete and A is in the class P, then P is equal to NP. So this theorem says that if you take an NP complete problem and you find a polynomial time algorithm for that NP complete problem, you would have found a polynomial time algorithm for all problems in the class NP. Thus, these problems are extremely prized problems in the class NP in the following sense. If you really want to show that P is equal to NP, then find a polynomial time algorithm for one of these problems. If you want to look for a candidate and you want to prove that P is not equal to NP, then NP complete problems are the prime candidates for being out of the class P. So in order to solve the P versus NP question, we will have two approaches. Suppose we find an NP complete problem A, and since A is the hardest problem in NP, so either we can try to prove that A is not in P. In fact, NP complete problems are the best candidates for that. The other alternative is to try to find a polynomial time algorithm for this NP complete problem A. If we succeed, then we will have shown that P is equal to NP. Well, no one has been able to do any of the above. No one has been able to resolve the P versus NP question. And no one has been able to prove anything about these approaches. Which of these approaches will succeed or fail, only time will tell us. Now, let us look at an extremely concrete question. So now we are looking at one concrete problem that we call satisfiability. Well, in satisfiability, what we have is some number of Boolean variables, x1 up to xn. And these Boolean variables can take either the value true or false. And of course, we sometimes denote true with 1 and false with 0. Using these Boolean variables, we can make what we call a Boolean formula. So by using the connectives and, or, and not, which you are very familiar with in computer science, we can make a very complicated or a large formula. So for example, I can just say a formula for you, which is x1 and x2 or x3. So this is a Boolean formula I just said, and this Boolean formula, what we can do is when we assign these variables different values, this Boolean formula becomes either true or false. Now suppose if I have 3 variables, then you know that I can assign 8 possible values to these 3 variables. So some of those values will make this formula true, and some of those assignments will make this formula false. Now, I'll say that the formula is satisfiable if there is at least one assignment of the variables which makes this formula true. And so a formula is satisfiable if I can find at least one assignment of the variables which makes the formula true. Let's go through these definitions formally. So once we have Boolean variables, we can make Boolean formulas. Let's first look at an example. Here's an example. Phi is equal to x1 or x2 in brackets, and that is ANDed with x4 bar or, and bracket open, x2 and x1 bar. So this is a Boolean formula. A Boolean formula is formally defined like this. We take the variables x1 up to xn and we declare that 0, 1 and xi are all Boolean formulae. And then we say that if phi and psi are 2 Boolean formulas, then so are phi and psi, phi or psi, and the negation of phi. So Boolean formulae are defined inductively. This is sometimes called structural induction, but what we're saying is that the basic Boolean formulas are the variables x1, x2, x3, any one of them is a Boolean formula, and the constants 0 and 1. And then by using the connectives and, or, and not, we can build formulas. And this is what we call a Boolean formula. Now an assignment of the variables is a mapping from the variables to 0 and 1, or true and false. Each assignment evaluates the formula to either 0 or 1 in a natural way. We substitute the values 0 and 1 and evaluate the formula by interpreting and, or, and not in the usual sense. So once I assign the variables, then I can find out whether the Boolean formula is true with respect to that assignment or not. Let's look at an example. Phi is the formula, it's actually x1 or x3 and x4 bar or x2 and x1 not. Now suppose if I take the assignment, I say x1, x2, x4 are 0 or false, and x3 is true. When I substitute these values for those variables in this formula, then the formula becomes 0 or 1 and 0 bar or 0 and 0 bar. So when I assign these variables to this formula, I evaluate it, I realize that the formula becomes 1 or true. So this particular assignment makes this formula true, and therefore I would say that this formula is satisfiable. So if for a formula there is at least one assignment which makes it true, we will call the formula satisfiable. If phi is the formula and tau is the assignment, then phi restricted to tau will denote the value of putting in the variables according to the tau in this formula and evaluating it. So now let's formally define what a satisfiable formula is. A formula phi is called satisfiable if there is an assignment tau such that phi assigned tau evaluates to 1. Note that if there is a formula with n variables, then there are potentially 2 to the n assignments. A formula is satisfiable if at least one of these assignments makes it 1 or true. So that's what is the definition of a satisfiable formula. Now we define SAT to be the collection of all Boolean formulas that are satisfiable. And it is very easy to see that SAT is an NP. So our theorem says SAT is an NP. By now you should be used to of the class NP. Well, how do I verify that a Boolean formula is satisfiable? Well, if you give me the satisfying assignment, I can then easily evaluate the formula with respect to that assignment and check whether that assignment leads to the value true or 1. Thus, it is very easy to come up with a verification algorithm for satisfiability, and hence this question is in NP. So the algorithm, I've written it down for you, we'll quickly go through it. Suppose that the algorithm takes the input phi and an assignment tau. Then it substitutes the variables of phi using the assignment tau and evaluates the formula. If the formula evaluates to 1, it accepts, otherwise it rejects. This is a verification algorithm for SAT, and it clearly runs in polynomial time. Thus, SAT is an NP. Now, the Cook-Levin theorem states that SAT is NP complete. So, this is the statement of Cook-Levin theorem. Every problem in NP can be reduced in polynomial time to SAT. Of course, we've already seen that SAT is an NP. So the only thing left to do is to prove that SAT is NP hard. And that's where the bulk of Cook-Levin theorem is, to show that every problem in NP can be reduced to SAT. Now, let's try to think how big of a result it is, and let's try to understand this result without going into the proof of it. We'll go into the proof of it in the subsequent lectures, but let's try to understand what this theorem says, the statement of it. It says that we have this class NP, and inside this class NP there's this one question called satisfiability, and every problem in that class can be reduced to it in polynomial time. It says a consequence of that is that if you can find a polynomial time algorithm for satisfiability, well, since everything is reducible to satisfiability, you would have found a polynomial time algorithm for every problem in NP. Thus, the whole class NP in some sense is being represented by this one very concrete problem. So, one of the consequences of the Cook-Levin theorem is that P is equal to NP if and only if satisfiability is in P. So, the question whether the class P is equal to NP all boils down to this one very, very concrete problem, satisfiability. If satisfiability is in P, if there is a polynomial time algorithm for it, then the class NP is equal to P. Otherwise, the class NP is obviously not equal to P. So, what Cook and Levin have done is taken a whole class of problems, and we'll see many other problems in this class as our lectures go on. They've taken a whole class of problems and squeezed it down to one problem of satisfiability. I'm very tempted here to use the metaphor of T.S. Eliot. What they have done is squeezed the whole universe into a ball, into one problem. And if this problem can be solved in polynomial time, then everything in NP can be. And if this problem cannot be, then of course P is not equal to NP. The goal of today's lecture is going to lead us to the proof of Cook-Levin theorem. In order to understand the Cook-Levin theorem and the proof of it, we have to understand what can be expressed in a Boolean formula. We will try to do this by first reducing one problem in NP to satisfiability. This will give us some feeling for satisfiability, and then we can go on to the proof of Cook-Levin theorem. So now what we will do is we'll take one little problem in NP and reduce it to satisfiability. And that little problem in NP will come from graph theory. It's called Threecolorability. Let me explain to you when a graph is three-colorable. So you can think of this as a very nice game, and you can play it with your friends. Take any graph, draw a graph which is just a bunch of vertices and edges, and now what you're trying to do is you're trying to color all the vertices of this graph with three colors. Let's say you take three colors, red, blue and green, so you have three colored pencils, and you want to color the vertices of this graph either red, blue or green. But the catch here is that you have to color it in such a way that no edge is monochromatic. What does that mean? Is that if two vertices are connected by an edge in the graph, then they must get different colors. So for example, if I give you a graph which is three vertices all connected to each other, then you can easily color it with three colors. On the other hand, if I give you a graph which is four vertices all connected with each other, then there's no way of finding a three coloring, because no matter how you color the graph, since you have four vertices, two of them will get the same color. But since I've said all these vertices are connected with each other, so you'll have two vertices connected by the edge, connected by an edge and having the same color, which is not allowed. Okay, so some graphs will be three colorable and some graphs will not be three colorable. Let's look at the problem formally. Let's say we are given a graph G with the vertex set V and E, edge set E. We say that G is three colorable if we can assign three colors, say red, blue and green, to its vertices in such a way such that the first requirement is each vertex is assigned exactly one color. And the second requirement is that if xy is an edge, then the color of x is different from the color of y. So if we can assign three colors to a graph such that no edge is monochromatic, we call the graph three-colorable. Now, this is a graph theory question. I can give you a graph and I can ask you whether the graph is three-colorable or not. Let's look at a few examples. Here is a picture of a graph that is three-colorable, and to show you that the graph is three-colorable, we have assigned each vertex a color from red, blue and green, and you can check that this is a proper coloring. So look at this picture, and what you can check is if there is an edge between two vertices, those vertices have different colors. They don't have the same color. So as you can see in this graph, no vertices which are connected by an edge have the same color. Let's look at another graph. Here's the picture of a graph that is not three-colorable. It is easy to see that this graph is not three-colorable since it has four vertices all connected to each other. Therefore, we need at least four colors to properly color it. What I mean by a proper coloring is a coloring of the vertices in which if two vertices are connected, they must get different colors. Let's look at another graph. Here is a picture of a graph, and once again I'm telling you that this graph is not three-colorable. In fact, it is not easy to see that we cannot color this graph with three colors. What you will have to do is look at this graph, stare at it for a while, and exhaustively check it at home that there is no way to three-color this graph. So, this particular graph that I have shown you, if you try to color it with three colors, no matter what you do, you end up coloring two vertices which are connected and giving them the same color. And therefore, we say this graph is not three-colorable. So, if I give you a graph, it may be three-colorable or not. And the three-colorability question is to take an input as a graph and be able to tell whether the graph is three-colorable or not. So formally, the language 3-color is defined to be the set of all encodings of graphs that are 3-colorable. So let us define 3-color to be the set of all G such that G is 3-colorable. So the 3-color problem is just that you will be given a graph as an input, and what you want to do is you want an algorithm that will go through that graph and tell you whether it is possible to color the graph with 3 colors. And remember, when we say color the graph in 3 colors, there's a restriction. No 2 vertices that are connected are allowed to get the same color. If you think for a moment, you would realize that this problem has an easy polynomial time verification algorithm, and therefore this problem is in NP. I'm not going to go into the details of the algorithm, the verification algorithm, or the proof that this problem is in NP. I will leave that as homework for you. So your homework is to come up with a polynomial time verification algorithm and show that the 3-color problem is in NP. So this problem is just one problem in NP. And if we believe the Cook-Levin theorem, then this problem is reducible to SAT. And that's what we are going to try to prove now. So we will prove the following theorem today. The theorem says that 3-color polynomial time reducible to SAT. Let's first try to understand what this means. We do not want to do any of the following 2 things. We do not want to design an algorithm to solve SAT. We do not want to design an algorithm to solve 3-color. What we want is to establish a relationship between 3-color and SAT. Let's think for a moment. Here's the problem 3-color and here's the problem SAT. Well, many computer scientists believe that both these problems are very difficult problems in the sense that we may not be able to find polynomial time algorithms for either of these problems. We'll see why that is the case later on, but we have 2 very hard problems. What we want to show is we can convert one problem into another easily. Thus, this 3-color problem can be reposed into a satisfiability question, and that is not very difficult to do. However, solving 3-color may itself be very difficult, and solving 3-set on itself may be very difficult. But it's easy to convert the 3-color problem into satisfiability problem. So what we want is a polynomial time algorithm that will take as an input a graph G and output a Boolean formula phi such that G is 3-colorable if and only if phi is satisfiable. So in some sense, you can view reducibility, polynomial time reducibility, as some kind of a translation scheme. What it does is allows us to translate one problem into another, and if we can do it quickly, that is in polynomial time, then we say that one problem is reducible to another, and we will do that with 3-color and SAT shortly. What we really want to do is come up with a translation algorithm that translates the problem of 3-colorability to satisfiability. In fact, given a graph, we want to be able to come up with the formula phi that is true if and only if the graph is 3-colorable. For that, let us see what can the formula phi will it have to say. So think about a graph that you have in mind, and what you want to do is come up with the formula phi. Well, this formula will have to say that the graph is 3-colorable. Whatever say means, and we'll see that we can express things with Boolean formulas. But if this formula can express the fact that the graph is 3-colorable, then we would be home. So how would this formula express that a graph is 3-colorable? What does it have to express? Well, the formula phi will simply express the following 2 things. It will say that it is possible to assign each vertex exactly one color from red, blue, and green. Furthermore, it will say that if 2 vertices are connected, then they will get different colors. So the formula phi will simply say that the graph G is 3-colorable. Now we have to do this in the language of satisfiability, in the language of Boolean formulas. Let's see how that can be done. first what we want to do is explore the power of satisfiability or Boolean formulas and see what kind of things we can express. Let us look at this following very simple formula, x1 or x2. This formula is true if and only if either x1 is true or x2 is true. So what I can do is, I can say that this little formula expresses the fact that either x1 is true or x2 is true. So this is what is being expressed by this formula. Now let's try to come up with a formula that is true if and only if exactly one out of the variables x1 and x2 is set to true. So now we want to come up with a formula which is true exactly when exactly one of the variables is set to true. So at least one variable should be set to true, but not both. Can we do that? Can we come up with a formula? Think about it for a moment and you would realize, yes, we can come up with the formula. This formula is x1 or x2 and the not of x1 and x2. So the first part, x1 or x2, says that either x1 has to be true or x2 has to be true. So in some sense, it's saying that at least one of them should be true. The second one is saying that both of them cannot be true. Both of them cannot be true simultaneously. So first part of this formula says that either x1 is true or x2 is true, at least one of them has to be true. The second one says both cannot be true. So if you put these things together and take the AND of them, the formula says that exactly one of x1 or x2 has to be true. Now let's do something slightly more complicated. Now what we want to do is go a bit further and come up with a formula which is true if and only if exactly one of the three variables x1, x2, x3 is true. So now I have three variables and I want to come up with a formula which will be true if and only if exactly one of the three variables is true. How can I express that? Well, we did that with two variables previously, but for three variables it's a bit more complicated. I'll make the formula in, once again, two parts. The first part will say at least one variable is true, and the second part will say that two variables cannot be true, and any two variables cannot be true. So let's look at that formula. It says x1 or x2 or x3, and that's the first part. It says that at least one of these variables must be true. And there's an AND there, and it says x1 and x2, the negation of that, which says that x1 and x2 cannot both be true. The third part of it says that x1 and x3 cannot both be true, and the fourth part says that x2 and x3 cannot be true. So it says that at least one of the variables should be true and no two can be true. Okay, so this is a slightly more complicated formula, and you can read this formula formally. It is x1 or x2 or x3 ANDed with not of x1 and x2, ANDed with not of x1 and x3, ANDed with not of x2 and x3. That's the formal way of reading this formula. The intuitive way of reading this formula is, this formula simply says that out of these three variables, exactly one is true. This formula is true when out of these three variables, exactly one is said to be true. Now, this is telling us the kind of things that we can express using the language of satisfiability. Now, let's explore satisfiability a bit further and see what we can do. Now, suppose that I have given to you a graph. Remember, we're trying to reduce threecolorability to satisfiability. And in order to do that, we'll have to play with both concepts. One concept is from graph theory, the other concept is from Boolean logic. We'll have to connect them somehow. So we'll have to understand what satisfiability is, and we'll have to understand a bit about graph theory. So now suppose that you're given a graph, and let's take a concrete example. As an example, let us take the graph whose vertex set consists of A, B, C, D, and E, and the edges are as follows. A is connected to B, is also connected to C and D. B is also connected to D, and D is connected to E. So you can see a picture of this graph. What I want to do is now somehow say that this graph is, somehow be able to come up with a formula which which will be true if and only if this graph is three-colorable. So I will do that in pieces. I'll break the thing up into pieces and come up with Boolean formulas, and in the end add them all together. Let's see what we're going to do. Well, suppose that I concentrate on the first vertex A, and let us say that I take three Boolean variables RA, BA and GA, which I give them the following interpretation. If RA is true, that means A is colored red. If BA is true, that means A is colored blue. If GA is true, that means A is colored green. So I have three variables, one for each color. For this given vertex A, I have RA, BA and GA, and if this color is going to be colored red, I'll set the variable RA to be true. If this vertex is going to be colored blue, I'll set the variable BA to be true, and if it's going to be colored green, I'll set the variable GA to be true. That's my interpretation. Now remember what a proper coloring was. Each vertex must be assigned a single color. When you're coloring a graph, you're not allowed to give one vertex more than one color. Furthermore, you're not allowed to leave any of the vertices uncolored. Well, what does that mean? That means in terms of these Boolean variables, this means that out of RA, BA and GA, exactly one variable must be true. How can we say that? Can we come up with a formula which is true if and only if a vertex is assigned exactly one color? Well, we've already done that. Let's look at it and re-look at it and see why does it express the fact that the vertex A gets precisely one color out of these three, red, blue and green. The formula is given to you. We remember our previous formula, which was saying that out of these three variables x1, x2 and x3, exactly one of them has to be true. The formula was x1 or x2 or x3, and it with x1 and x2, the negation of it, and it with these two other things. So we remember this formula. Our new formula will be modeled after that. So our formula is going to be RA or BA or GA. So the first part says that A must get at least one color, either red, blue or green. The second part says, and not of RA and RB, which means that it cannot simultaneously be both red and blue. The third part says, not of RA and GA, which says that it cannot be red and green simultaneously. And the last part says that it cannot be blue and green simultaneously. So this long formula says that the vertex A must be assigned exactly one color out of red, blue and green. Now, I can play the same trick with the second vertex B. I can just make three variables, RB, BB and GB, and just come up with a formula which will be true if and only if the vertex B is assigned exactly one color out of red, blue and green, and I've written that for you. So this second formula looks exactly like the formula written above it, but instead of A it has B because it's talking about the vertex B, and this is true if and only if B is assigned exactly one color. So it's easy to find a formula that is true if and only if a vertex is assigned exactly one color. Now let's go on to the second part. Now let's consider an edge. How can we find a formula that is true if and only if the vertices A and B are given different colors? Remember that in three-color problem, we want to color the vertices of the graph in such a way such that if two vertices are connected, they must get different colors. Can I come up with a Boolean formula to express that fact? Can I come up with a Boolean formula that is true if and only if someone has assigned these two vertices different colors? How can I write that? Well, that's very easy. Let's look at the formula. Suppose I want to say that I have an edge between A and B, and I want to say the vertices A and B should get different colors. Well, that's easy. What I will say that not of RA and RB, which means that A and B both can't be assigned the color red, and not of BA and BB, which means they both cannot be assigned the color blue, and not of GA and GB, which means the vertices A and B cannot both be assigned the color green. So what I'm saying, you cannot assign A and B both the color red, you cannot assign A and B both the color blue, and you cannot assign the vertices A and B both the color green. So that is equivalent to saying that you must assign A and B different colors. So using satisfiability, I've been able to express two things. One is each vertex must get a unique color out of red, blue and green. Two is if there is an edge, those two vertices must get different colors. Well, now if I AND all these formulas, what I will do is be able to express that the graph is three-colorable. I'll come up with a formula which will be satisfiable if and only if the graph is three-colorable. Let's look at that. We have learned two things. Given a vertex V, we can make three variables RV, BV and GV and make a formula that says V is assigned exactly one out of the three colors red, blue and green. Given an edge U, W, we can come up with a formula that is true or says that U and W must have different colors. What happens if we put them all together? Let's see what we get. Let's look at the formula. And here we are given a graph G with vertex set V and edge set E, and we consider this formula, which looks like a very gigantic formula, but it's nothing but pieces of it we've studied already. This formula is denoted by phi sub G, and it's the AND of two parts, and the first part is a big AND, and this big AND says that is ANDed over all vertices of the graph. And if you look inside the bracket, that is just the formula which is true if and only if the vertex V is assigned a unique color out of red, blue and green. And since I'm ANDing it over all the vertices, I'm saying each vertex must be assigned a unique color out of red, blue and green. So any assignment that makes the first part of this formula must correspond to a coloring of the vertices in which each vertex is assigned a unique color out of red, blue and green, and no vertex is left uncolored. Let's look at the second part of the formula. Let's break it down. Inside it, there's an AND over all edges of the graph. So it's saying this condition must be true for all the edges of the graph. And what's the condition inside the brackets? It says that, well, if A and B were connected, then they cannot have the same color. So the second part of this formula will be satisfied if for each edge the thing in the brackets is satisfied, because these are all ANDed together. And each thing in the bracket is saying for every edge, the vertices that are connected by that edge must have the different color. So now, to make this formula phi true, I must find an assignment which satisfies the first part, which corresponds to finding a coloring of the vertices which gives a distinct color out of red, blue and green to each vertex. Furthermore, for me to satisfy the second part, it must be the case that if two vertices are connected, they get a different color. So this formula will be satisfiable if and only if the graph is three-colorable. If a three-coloring exists, what I can do is assign that three-coloring to my graph and set the corresponding variables to be true and satisfy this formula. On the other hand, if such a coloring does not exist, I will never be able to satisfy this formula. So this is a formula which is satisfiable if and only if the graph is three-colorable. So the formula actually says that the graph is three-colorable. It is satisfiable if and only if we can find a three-coloring of G. Once we have done that, and note what we were doing, all we have done is translation. What we did was we took a problem in graph theory and converted it to a satisfiability question. I can give you a graph and ask you, is this graph three-colorable? Or I could write down this formula corresponding to this graph, and this formula is a Boolean formula, and I can ask you whether this Boolean formula is satisfiable or not. They are equivalent questions. So if you give me a graph, I can convert that into a formula. If the graph is three-colorable, the formula would be satisfiable. If the graph is not three-colorable, the formula would not be satisfiable. And this computing this phi is what our reducibility is. So what we have done is shown that three-color is reducible to satisfiability. Let's look at the formal algorithm which reduces three-color to satisfiability. Well, consider the algorithm. It takes as an input a graph G, and it computes phi of G and outputs it. This algorithm satisfies all requirements of a polynomial time reducibility. Why does it do that? It's easy to see that the formula phi sub G can be easily computed in polynomial time. Furthermore, if the graph is three-colorable, the phi of G, the formula we get, will be satisfiable. If the graph is not three-colorable, the formula phi of G would not be satisfiable. So what we want to note is we have not done any of the following. We have not said anything about how hard it is to solve the satisfiability question. We have not said anything about how hard it is to solve the three-color problem. On the other hand, we have shown that in polynomial time we can reduce the three-color problem to the satisfiability question. Well, this little theorem has a consequence. Well, what is the consequence? The consequence is that if sat is in P, then three-color would be in P. So the problem, satisfiability problem, in some sense is harder than three-color problem, because if we find a polynomial time algorithm for satisfiability, we would also find a polynomial time algorithm for three-color problem. What would be that algorithm? Well, that algorithm would be reduce the three-color problem to SAT and then use the polynomial time algorithm for SAT to solve the SAT problem, which will give you the answer for the three-color problem. Of course, no one knows of a polynomial time algorithm for either SAT or three-colorability. This was just hypothetically saying that what we have shown is satisfiability is a more general problem than the three-colorability problem. So the little theorem that we have proved is that three-colorable is polynomial time reducible to SAT. Now let us compare this theorem with the Cook-Levin theorem. The Cook-Levin theorem says every language A in NP is reducible to satisfiability. Three-color is one language in NP, and we showed that it was reducible to SAT. But the Cook-Levin theorem says much, much more than that. It says there's nothing special about three-color. You could have picked any problem in NP and that would be reducible to SAT. So what we have done is shown one reducibility. Well, the Cook-Levin theorem is talking about infinitely many problems that are reducible to SAT. That's why it's such a powerful, such an important theorem. Thus, the Cook-Levin theorem is much more general, and to prove the Cook-Levin theorem, we will need to understand satisfiability, non-deterministic Turing machines, and reducibility in a lot more detail. So, in the next lecture, what we would do is we will start the proof of Cook-Levin theorem. Let's see why what we have done is much, much simpler than what the Cook-Levin theorem says. Well, remember the three-color problem? That was a problem in graph theory. We knew a lot about this problem. We knew exactly what the problem was. And we used our knowledge of graphs and our knowledge or whatever we understood about satisfiability to come up with the reducibility. The Cook-Levin theorem, to prove that, we will not have that luxury. It doesn't talk about only graph theoretic questions in the class NP. It doesn't talk about scheduling problems that are in NP. It doesn't talk about some kind of subset sum type number theoretic problems that are in NP. It says any problem in NP is reducible to SAT. So what we know about these problems is very little. Yet that knowledge is enough for us to show that there is a reducibility from that problem to SAT. We will start the proof of the Cook-Levin theorem in the next lecture. I'll see you next time. Thank you and goodbye.